Hello, today we're going to talk about the magnitude of the equilibrium constant. So remember that your equilibrium constant expression, you always put the products on the top and the reactants on the bottom. So that means if you're looking at the value of K, when K is greater than 1, that means you have more products because you have more on the top of that ratio. Then if you have more reactants, you'll wind up with a value of K that is less than 1. You have more on the bottom of the fraction. Now, when we're looking at the extremes, when you have K that is very, very big or very, very small, it will really go to the extremes of the reaction as well, reactants, products. If K is much, much greater than 1, so like 1,000 or more, that means almost entirely it's made up of just products. That means you have very, very few reactants, and so it essentially goes to completion. Right? You might have a couple particles of reactants left over, but it essentially goes to completion. Now, the reverse is true as well. When you have K, a value of K that's very, very small, so 0.001 or smaller, that means you have almost entirely just reactants present. You might have a few particles of the products present, but very, very few. So the reaction barely proceeds at all in the forward direction. So again, I think it's useful to just either write your expression out all the way, or at least write this little cheat sheet so you can see that products are on the top, reactants are on the bottom, and you can see how that affects your ratio depending on whether you have more reactants or more products. Okay, so for this reaction, this generalized reaction, we have A plus B yields 2C plus D, and they gave us the value for K as 1.34 times 10 to the 7th. Remember, there's no unit for K because it's just a ratio. So we can see that this value is extremely large. That means it greatly, greatly values the products. And if we write our little brief expression there, products or reactants, we know that there's much, much, much more products than reactants. So we know that it's going to be almost entirely C and D, and very, very few, if any, of A and B. So at equilibrium, you're going to have the least amount of reactants of the A and B, and then you will have much more D, and then a lot more C. And that's because you have twice as many C's formed for every D stoichiometrically. But you'll have much, much, much more of both of the products than any of your reactants present. And here's another example question. So if I have 2A plus B, it yields 2C. They give us a K value of 5.27 times 10 to the negative 4th. It's a very small number. Remember, K is always products over reactants, and if it's very small, that means I must have a lot more reactants. Now in this one, it says if I have 1 moles of A and 1 moles of B were placed in a 1 liter container and allowed to reach equilibrium. That means I don't have any C to begin with. Okay. But what would be true of the partial pressures of the gases at equilibrium? All right. Remember that pressure and moles are directly related, so even though they give us moles, they're asking about partial pressure. That's okay. Now, we need to look at both the value of K and the stoichiometric mole ratio. It barely forms any products at all because K is very small. So you're going to have the least amount of C. So we're not going to talk about A or B. E might be true depending on how much you have, but it might be true if your K value was closer to 1. It doesn't have to be exactly 1 because of the coefficients affecting your equilibrium expression, but because it's so small and so far away from 1, I would not choose E either. So C is very small in comparison to A and B. Now, even though we started out with equal amounts, the reaction will proceed in the forward direction just to a very small extent. But since it does, A is used up twice as fast as B. So A will be just a little bit smaller than B Not a super significant amount, but enough that it's going to make me choose C instead of D for this example.